What are gravitational waves? It all starts back in 1915 with Einstein. He hypothesized that all objects with mass would warp the fabric of space-time. If their mass is great enough, those distortions could cause other objects to fall into them. This is what we call gravity. Einstein also predicted that these distortions could travel across the universe, stretching and squeezing space and time as they move. And this is what we call gravitational waves. Later, researchers realized that if two particularly giant masses, like two black holes, are trapped in each other's gravitational field, they should start to spiral in towards each other, and so would the distortions they make to space-time. This would create gravitational waves which would travel away from the objects like ripples in a pond. But as these gravitational waves travel through space, they'd become more and more difficult to detect. In fact, Einstein thought scientists would never see them, but that hasn't stopped them from trying. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. This is a conceptually simple piece of kit that aims to measure the distortion in space-time caused by gravitational waves. LIGO works by splitting a laser beam and sending it in two directions. The beams travel precisely the same distance down long vacuum tubes. They're reflected off mirrors, and then they come back and recombine. The light waves of each laser beam are made to exactly line up so that they cancel each other out, and nothing will reach the light detector at the end. But if a gravitational wave passes through, it will minutely distort space-time, changing the distance each laser beam has to travel. That will mean that the waves no longer line up, they won't cancel each other out, and the signal will be detected. The experiment is hypersensitive to disturbances, and so two identical LIGOs were built on opposite sides of the United States. Both will have to get the same reading at the same time for any signal to be considered valid. LIGO is designed to directly measure gravitational waves. This is different from another experiment based at the South Pole called BICEP-2, which made headlines back in 2014. BICEP-2 is also looking for gravitational waves, but not directly. Instead, it looks for the imprint gravitational waves would leave on the cosmic microwave background. That's the afterglow of the Big Bang. LIGO, on the other hand, is looking for much more recent gravitational waves, created only a few 100 million years ago, by something like the collision of two neutron stars or the merging of two black holes. It's been almost exactly a century since Einstein first predicted the existence of gravitational waves. And now, with LIGO, we may finally be able to tell if he was right.